Welcome to the lecture on considerations in aqueous modeling. So, we will talk about the issues and which are considerations which are required in the case of aqueous modeling or water modeling. So, we will talk about the different aspects in this lecture. So, coming to the issues or considerations which are required as we have discussed in the past, that the first thing is the consideration about the scale factor. So, as you know that you need to have the selection of proper scale. You have seen that if you try to have the similarity criteria using the Reynolds similarity or the Froude similarity, you have the different many a times you get if you talk about the velocity of the model. So, as compared to velocity in the actual case, you will have that in the function of either 1 by lambda or under root lambda. So, if the lambda is the scale factor. So, now the thing is that many a times the both can be satisfied only when the lambda is 1. So, that becomes very expensive, means your model has to be of the same size as that of the prototype. So, it will become very expensive. So, so basically in the starting point in a physical model investigation is the choice of the appropriate geometric scale factor, and you will have that basically determines the size of the model vessel. For turbulent flows, the fill factor has not to be very small. Now, as we see that the full scale models, if you try to have the try to satisfy both the similarity Reynolds as well as Froude. So, you will have to have the lambda is 1, and then in that case you will have the very large model, and that will be very expensive. Then when you are talking about the turbulent flow. So, if you take very small scale factor, in that case it may not represent actually the flow which is taking place. So, that is because that is not going to create the turbulence, enough turbulence inside the Tundis. So, because as the vessel size is decreasing, the importance of Reynolds number relative to Froude number is increasing, and that is why you will have to have the properly you will have to see that what should be the actually the scale factor. So, once you come to decide about the scale factor, then next comes the choice of the working fluid. Now, if you talk about the working fluid, so this is a very important consideration, because there are many kind of fluid, but then you will have to look into those aspects that which is readily available and which satisfies those conditions. So, water at 290, now it has been found that when you take water which is at 298 K or about 25 degrees Celsius, that is your normal room temperature, and if you take the molten steel at 1873 Kelvin. So, what has been seen that they have nearly the similar kinematic viscosity, that is mu by rho, and that is why it very much helps ensure that you have the similar flow regime established in both the model as well as in the actual Tundis. Then also flow phenomena in steel making systems are that is why they are frequently investigated through these water models. So water is taken as a very most acceptable kind of fluid which is used for the modeling studies in case of the steel making operations. So there are many reasons for water being selected as the fluid, working fluid, and those reasons are that water is cheap and also it is readily available. So you can have water at all the places. So that is why it gives you a very good choice to have the water, otherwise other things will be costly. It is convenient to work with water because it is non-corrosive, it is also neutral, and it has many of the qualities which make it very good for handling. So you can use it with much of ease, and that is why it has a lot of advantage over other fluid. It has low capital and operating cost of the model. So if you are making the model with working fluid as water, then certainly you have the requirement of low capital cost as far as the working fluid is concerned, and also you will have low operating cost of the model. Also this is also one of the very important property of the water, that you, because being the transparent, if you keep that system, if you make the physical model with the perspex sheet, in that case you can have easy visualization of the flow if you have water flowing inside the vessel. So that that is further giving you another added advantage, and that is why these are the reasons because of which you are taking the water as the most popular working fluid. So in isothermal flow modeling, the operating parameters are determined solely from the dynamic similarity criterion, while both dynamic and thermal similarity criterion are considered for the non isothermal situations. You have already we have discussed that when we talk about the isothermal system, in that case you have the dynamic similarity criterion solely to be taken into account, but when we talk about the non isothermal situations, in those situations what we see is that you will have to have the thermal similarity, you have other non dimensional numbers coming into picture, and they also, that condition also need to be met in those situations. So what we see is that normally what we see that when we talk about the Froude number, so it is a function of the velocity and length. So you know that the Froude number, which is nothing but the ratio of the inertial to the the gravitational force. So you will have the velocity and length will be there, and you will have the thermophysical properties which are there, like velocity or density. So they are expected to exert a lot of effect on the flow which is Froude dominated. So that is why what we see is that that any liquid in principle can be used to represent this molten steel flow in that Froude dominated flow regime. Now many a times as you have discussed that we are taking the water as the most acceptable working fluid. So what we do is we do the scaling, and then we do make the models, the physical models based on those scaling factors. So, for example, if you see that you may be having the situation like you are told that you are to make a physical model and you are given the scale factor also. So, suppose you are given the scale factor and you are going to make a 1:3 model. So, 1:3 means 0.33 is the scaling. So, suppose you have to make one industrial stirred ladle. So, for the ladle, if for that industrial size ladle, if the height of the ladle is given as 3.1 meter. Similarly, if your filled liquid depth, so that is given as suppose say 2.7 meter. So, that will be total height is 3.1 and the height up to which the liquid has been filled, that is your 2.7 meter. Then if you say it is given that if it dia at the base, it is given as 3.58 meter. Similarly, dia at the top, so it is given as the 4 meter. So, and then you have the gas flow rate. So, that is in case of that is Newton meters cube per second, and that is given as 1.1 into 10 to the power minus 2. Then you have a porous plug dia which is there in this case. So, that is given as 140 and mm. So, this is in terms of millimeter, and also you have dimensionless plug location, porous plug location. So, that is 2/3 r. So, now if you talk about the making the model, in that case if you take the scaling factor, so you can have the height as height of the model ladle. It will be something like you will have lambda into h prototype. So, it will be 0.33 multiplied by 3.10. So, it will be you will have or 1/3 you can have, or if you multiply with 3.1 into 0.33. So, it will be 1.023 something like meter. So, if you go to the diameter of the diameter at the base of the model, so you will calculate as again lambda into diameter of the prototype at the base. So, diameter at the base of the prototype is given as 3.58. So, it will be 0.33 into 3.58. So, it will be 1.18 meter. Similarly, you will have calculation of other parameters, like you have the diameter at the top of the model. It will be lambda into diameter of top of the prototype. So, diameter at the top of the prototype will be 4 meters. So, it will be 0.33 multiplied by 4. So, it will be 1.32 meter. Similarly, the liquid filled in the up to what height in the model, it will be again lambda times liquid filled for the prototype. So, this way you can calculate. So, it will be liquid filled is up to the height of 2.7. So, it will be 0.33 into 2.7. So, it will be 0.891 meter. So, this way you can have the value of these model what you see that in this case the location will be still maintained at 2 by 3 r, because you are anyway changing. However, this porous plug this diameter, so this need not be changed, because this is basically this diameter of that gas injection device, that need not be changed, because what happens that these stirred ladles are normally the potential energy driven. So, we can have their value as the same one, and what you can see is that you can have the calculation of the Froude similarity. So, you can have the Froude similarity criteria, and you can see that how they are matching. So, that is the use of these scaling factors in finding, and if you try to have the value of other parameters also, you can calculate, like you can calculate for the Q also. So, that also can be calculated, and even the isothermal and non-isothermal conditions may also be taken into account. So, this way the use of these scaling factors is there in the case of modeling. Now, coming to the limitation of the aqueous modeling. So, now there are certain limitations to this water modeling also, because many a times we are taking. So, as we discussed that on many accounts we have to have certain compromises. So, small scale factor flow idealization in terms of Froude number, Prandtl number difference between water and liquid still etc. are inherent in case of water modeling, and create the uncertainties, because if you look at the physical properties of water and the steel, so you will have the differences in these number values, and they are going to inherently cause certain kind of uncertainties in the case of aqueous modeling, when we are taking water as the working fluid. Inability to realistically represent the multi-phase nature of a steel making system. So, as we see that when we talk about the steel making system, so what we see there, that you have the molten steel at the bottom, and then you will have the presence of the slag, and then you have the air also, and they will be interacting. So, they will have interfaces in between them. So, it is basically a multi-phase system kind of environment which is there. Now, you cannot realistically, you cannot go very close to the actual system, because it is very difficult to have the similar kind of system, because that is at a very high temperature, where you will have the molten steel, and then above the steel you will have the molten slag. So, you cannot realistically represent these multi-phase nature of the steel making system in a very realistic manner. So, that is basically one challenge which is there, or one concern. So, that is the limitation. So, many people have tried to even take into consideration things like you give certain wood floor or so at the at the surface of the water. So, that may represent the slag which is there in the steel making vessel like Tundis or ladle, but that is not the true representation. That will not truly represent the situation which will be there inside the Tundis. So, that becomes a challenge in the case of the aqueous modeling. In many water model investigations, the presence of an upper slag phase is entirely ignored. So, what we do normally, that we are ignoring this slag level. So, when we are going for the solution, because when we do the physical modeling, so based on the physical modeling results, and we also so these results are used to validate first, and then we try to have the results from the numerical investigation. Now, as in the normal case, you will have the slag present above the molten steel, and that is basically ignored in most of the cases. So, so ignoring this slag phase is the only way by which you can ease the computational method or solution methodology when you are modeling through the numerical means. So, so in many water modeling, because you do not have actually that kind of material which should represent in fact the slag, which should very much replicate the kind of event or the kind of activity which is done by the slag at the top level of the steel. So, that is many investigators have tried to do it through the use of either the wood floors or so, but then in most of the cases we try to ignore it. So, so that certainly leads to certain kind of error, and that is one of the limitation of this aqueous modeling, which is seen which is still researchers are trying to have the they have cases by which they can replicate these slag flow also. Slag can be taken into account. So, that is one challenge. Physical processes occurring in a high temperature steel making system involving metal slag gas are impossible to be recreated in water models. So, as we discussed that it is very difficult to have the recreation of that system which is in actual present in the steel making case, like you have the metal, then you have the slag, and also you have the gas. So, it becomes a 3-phase kind of system, which is nothing but the multi-phase system, and you cannot make in water models, because the gas system is anyway impossible in such cases. So, that is becoming one of the limitation of the aqueous modeling. You have results of actual steel making process drawn solely from water model studies with or without buoyant phase are likely to be largely inadequate. So, many a times we go for the isothermal analysis, we are not taking the thermal analysis into account, because when if we talk about the actual system, so when the ladle basically is, suppose when ladle is, there is ladle changeover, the steel which the other ladle has given, or the temperature which is there of the steel in the turn disk, and the steel temperature of the coming ladle, they may be entirely different, and that may result into the buoyancy forces, and these buoyancy forces they affect the fluid flow which occurs inside the vessel. So, when we are talking about the water modeling, so in most of the cases we talk about the isothermal analysis, and in those cases we are neglecting these buoyancy forces, and that may not be truly representing the kind of phenomena which is going to take place inside the turn disk. So, that is another limitation of this water modeling when we do in the case of these aqueous modeling. So, these are the limitations in the case of water modeling. So, introduction to the experimental techniques which are used to study in the aqueous modeling, and you have many experimental techniques which are used for studying these flow modeling. Is the flow visualization, then you have measurement of velocity, you have turbulence and phases in two phase flows, and then you have heat and mass transport. So, these are the things which we need to study using the experimental techniques. So, if you come to the flow visualization, so what happens that in the flow visualization, it will be providing you the snapshot of the flow field, and it will be representing a useful tool for studying the instantaneous flow characteristics. So, what we do is that we normally make the Tandis model or the ladle model using a perspex sheet which is transparent, so that you can visualize the flow. And what we do is normally we put the tracer. So, and the tracer method is most widely used, and for that there are different procedures. So, you have the different way. So, one is the injection method. So, what we do is that in this case we inject certain tracer, and this tracer once injected it will go and it will be dispersed inside the vessel. So, that vessel is either it is Tandis or ladle. So, it will be going inside and it will disperse, it will diffuse inside the Tandis, and its concentration will be monitored at different points inside the vessel or at the outlet of the vessel or the Tandis or the ladle. So, normally when we talk about the this injection method, so in that we use certain tracer, and this tracer is normally a die. So, that is this we use a tracer or a die. So, this typically it is a die that is KMnO4. So, this is KMnO4 solution, or you have other neutral kind of buoyant fine particles which are used as the these tracer particles. So, they will be it may be silver coated glass bubbles also. So, that will be going into it, and they will be floating. So, they will be injected into the flow, and then their flow is observed. So, and that is being traced. Then you have the suspension method. So, here you will have the suitable suspended particle is there. So, you will have suitable tracers like small pieces of silk. So, its movement will be traced. So, that is also another one. By suspension you can have its trace. So, by that you can have the study of the flow. So, apart from that you will have the different flow measurement devices are applied to measure the velocity and turbulence, and in that you have Pettit tube, you have hot wire anemometer, laser Doppler velocimeter. PIV is very much used in the case of physical modeling, where you try to have the velocity profile at certain section. So, drag probe. So, these are the different ways by which you measure these velocity and the flow profile. So, this is how your velocity and turbulence and PIV setup looks like. So, in that case you find the the velocity profiles inside the vessel. So, this is about the physical modeling aspects, the issues and challenges with that, and when we talk about the case studies and when we talk about other aspects, then we will have further discussion about these topics, and we will have more clarity in our understanding. Thank you very much.